Welcome to the special edition episode of Beyond the Forecast. We're going to be talking about the Artemis 2, 3, 4 future missions to the moon, and this is all in a continuation episode with the interviews and conversations I had with the aerospace engineers at NASA Langley Research Center. Shout out to all of the scientists that are working on these teams, not just at NASA Langley, but at all the other centers for putting together such an amazing suite of missions that we have coming up. Here's a look at that timeline once again. So we have Artemis 2, Artemis 3, Artemis 4, 5, and beyond. That's going to bring our astronauts back to the lunar surface. Now in this episode, we're going to be talking with Kylel Scott. He's part of the imaging and processing data analysis team at NASA Langley Research Center. He worked on some of the data that they captured with Artemis 1 and Orion as that re-entered back into the atmosphere. They're also going to be focused on this upcoming and Artemis 2 mission and the future ones too, to really see what is happening as these spacecraft come back through Earth's atmosphere. So this is a really insightful and kind of cool conversation that they're focused on, and this goes all the way back even to the shuttle era as well. And then in addition to that, we're going to be talking with Jessica Friz and Jacob Martin, and we're going to be going into their laboratory as we look to the future of Artemis and getting that long-term presence on the moon. So without further ado, let's get into that first talk and conversation. Here's Kylel. We're going to keep the interview roundtable going here at NASA Langley Research Center. Kylel Scott, you're an aerospace engineer and scientist. You've been working with imaging and really focusing on SLS, the Orion capsule. Give me an overview of what your team has been doing here at NASA Langley.
Yeah, so my team is actually kind of a continuation of a team that was started in the shuttle days called HiTherm, where they specialize in putting airborne and ground-based platforms up to image the space shuttle, the ISS during some of its construction, and then they evolved into SciFly, which specializes in putting imagery and cameras on airborne platforms to image different rocket launches and capsule returns. We imaged Lofted, which was a NASA mission, but we've also worked with SpaceX, Blue Origin, and a number of other companies outside of NASA to kind of help collect meaningful data for some of those organizations.
So starting all the way back to shuttle, we're not going to talk so much about that right now, but when we're looking ahead now to SLS, we saw Artemis 1 already launch. What did you learn from that? What did your team learn from that? And what are we looking at for Artemis 2?
Yeah, that's a great question. So we imaged the launch of Artemis 1 and then the re-entry of the Orion capsule for Artemis 1 after the mission. And for the launch, we saw really good success. We actually deployed, it was our first observation deploying one of our novel payloads, SAMI, or the SciFly Airborne Multispectral Imager, that collects data in one big package about this big from the visible to the midwave. So we got the launch in visible to midwave, and we were able to basically calibrate our data and get temperatures on the surface of the vehicle, which the people who make the vehicle then use to determine whether or not how they made it actually suffices for the conditions that they expected it to be under. So we did that for the launch and then for the reentry as well. So at the time we were testing the Orion capsule without people in it, and one of the biggest things is the TPS, or the thermal protection system.
So that would be underneath this layer right here, because this has an engine bell and a little fuel tank, but this would be, if we were to slice off right here, that's where the heat shield would be, and that's where the thermal protection would be, correct?
Exactly, yeah. So the capsule kind of comes in once these two detach like that, and then this cylinder or conic shape kind of comes in with the heat shield part going towards the direction that it's traveling. So the heat shield is actually what protects whatever's inside from the thermal environment outside when it's coming into the atmosphere. So understanding how well that's performing is essential, because if it breaks down at all, then obviously the things that are inside can kind of see the impacts of those in real time. So we were out there imaging the reentry of the thermal protection system. That was our imaging objective. And we learned a lot about how it was constructed, things that were happening during flights, things that were coming off of the heat shield that were expected, and things that were happening a little off nominal during Artemis 1 that we then essentially, again, calibrated that data gave it to some of our customers, and they used that to kind of iterate on the design for Artemis 2 and beyond.
How do you image, we've been talking about imaging, how do you image these things? Is it just taking pictures, or what is it?
Yeah, that's a great question. So we have like a really wide arsenal of assets that we can use, different aircraft with different kind of capabilities in terms of how high they can fly, how far they can fly, and then all these aircraft have different payloads or cameras that collect different kinds of data. So obviously you have like your camera, kind of your point and shoot with the spatial, and you can do that obviously in the visible spectrum, but in different infrareds. We also collect data with spectrometers, which kind of are a little bit different. They don't collect spatial data, but they collect stuff along the spectrum. And we use all that data to understand things like temperature of whatever we're looking at, as well as spatial like characteristics if things are liberating off. All of our sensors are very high resolution and very high frame rates. So we can record some of these events at like 120 frames a second or more, and spatial resolutions up to like 6K. We have a lot of data that we've collected of just like looking at the moon and seeing like individual craters and spots. So when it comes to observing like a reentry capsule, we get terabytes of data that we can go through and reduce into temperature or take trajectories from some of the liberated particles and understand like when and how those are kind of moving in space. And all that stuff is really useful for the people who are actually building those systems.
That's fascinating. So why are I know the visible spectrum, but infrared, give me some more insight. Why the infrared?
Yeah, so the infrared is key for understanding temperature distributions. So for reentry vehicles like a capsule, like the Orion capsule, the biggest thing is when it comes back into the atmosphere, it's going to be subjected to a lot of aerothermal and aerodynamic pressures and factors that will have a direct effect on the structural integrity of the capsule.
Because I remember we did an earlier episode about Apollo 12, and that came into the atmosphere at 24,000 miles an hour. Yeah. Now a typical spacecraft that goes to the International Space Station will have a speed of around 17,000 miles an hour just coming back, because you don't need to be as fast in orbit. Yeah. But for Orion, that came in really fast too for the first Artemis 1 test. Now with Artemis 2, I would assume pretty similar, right?
It is pretty similar, yeah. And there are a number of reasons why that happens or why that needs to happen, and as fast as it is, and also at the angle that it comes in. For Artemis 1, we tried out a different trajectory that we won't be doing for Artemis 2, where it actually skipped off of the atmosphere, or the upper layer of the atmosphere, and came back down in order to slow it down a little bit. But the infrared...
So how do you do that exactly, the skip? So here's the Earth, and then let's say this is the spacecraft, and you're coming through, we're talking about the thermosphere, right?
Yeah.
Or are we talking even farther out?
That's about right.
Okay, so we're talking about the thermosphere, so we're coming in, and we're going to hit it, and then we're going to come back up, and then we're going to go back in?
Yeah, and the idea is that you can kind of use it to slow down, basically, instead of coming in straight at once. You then use the atmosphere to kind of slow yourself down before you go in for a second time.
Kind of like throwing a rock on the water to skip it.
Skipping a rock.
Yeah, you skip a rock, you just kind of come in at the right angle, you touch it, and then you come back down, and then,
Exactly, yeah.
Wow.
So, and all that, again, is to like make sure that space capsule is safe and is still, the structural integrity is really high and it's still like put together really well. So one way to validate that is obviously with sensors that are on board the capsule.
Okay.
And if you can think about the TPS surface that's right here, there are sensors that are embedded into the surface that help understand like pressure, density, or density of pressure around the TPS, the temperature, things like that on board. But they're usually pretty sparse, and sometimes they require a different kind of calibration. So that's what's called kind of like an intrinsic sensing modality. But we have like remote sensing modalities where we're maybe, if it's coming in here, over here on an airplane, and we can point our infrared sensors up to the TPS, get temperature measurements, and kind of relay that same or similar data to the people who are also looking at the embedded sensors.
Wow. So there's a lot of data, a lot of things we're going to be looking at, and you're going to be focused on with Artemis 2 coming up here.
Oh yeah, definitely.
What have you learned from Artemis 1 going into Artemis 2? Any changes or any tweaks that you've done with your workflow?
Yeah, we have actually improved on our like payloads and our assets. So we have a number of different aircraft that we're going to be using. For the Artemis 1, we were using just one aircraft, and we were focused on a specific spot during the reentry. Now we are going to deploy 3 to 4 aircraft, so we can focus on a lot more of the reentry and get really good high resolution data as it's coming throughout, which is a huge improvement. And then some of our data processing capabilities have improved so that we can track things that are essentially seen from those different perspectives and really piece together, kind of like forensic scientists, piece together what happened throughout all of our data that we're going to collect, the terabytes of data that we'll have, and it should be pretty interesting.
All right, well, we're looking forward to the launch.
Yeah, thank you.
Congratulations on your work, yeah, and thanks for working on it here at NASA Langley.
Thank you, thank you.
All right, we'll be back with more in just a little bit. We're here in the macro lab at NASA Langley Research Center. Jacob Martin and Jessica Friz, you've been in this room for a while working on a lot of different things in here. We're going to go through some of these things and show you what we're looking at, but we're standing in front of something really, really cool. So what is this?
Yeah, this is the Lightweight Surface Manipulation System, otherwise known as LSMS. It's essentially a robotic crane that's aimed at offloading payloads on the lunar surface or Martian surfaces, doesn't really matter that much, but it's for us to be able to provide logistics elements to surfaces for astronauts to use before they get there.
So the lightweight surface
manipulation system. So this is the scale that it would be if it were to be on the moon. This is one of the scales, yes.
One of the scales, yeah. So we could take cargo, you were mentioning earlier, taking cargo off of a spacecraft even?
Yeah, so we have a mock-up of a lander deck behind you, and the idea is you can take payloads like 400 to 500 kilogram payloads and offload those to the surface, and then astronauts can come and grab their water, their gas, their food from that pallet and bring it into their habitat.
I noticed that you're mentioning everything in kilograms. I appreciate
Yes.
that. It's a lot easier to do conversions. We'll do some conversions at the bottom of the screen if you need. But so this is one of the things. There's also smaller that we have down in the pits too. Want to go check those out?
Yeah, so let's go this way. We have some in one of our two pits here, which is really nice for this lab. It lets us use different levels of operations because obviously we need to simulate that lander deck. And so down here in the pit, we have a small version that lets us do software development and operation development to ensure we can do offloading safely. And then we scale back up to the larger systems to do autonomous operations for payload offloading.
Yeah, that's going to be a big thing because when we're going to land the spacecraft, that's going to be in one spot where the base is going to be in another spot. It's not going to be like, oh, let's land 10 feet away from our building. You can't do that on the moon. Right. It's a little too close. You have stuff flying away from the landing, that plume. So that's an important thing that we're going to have to do. And you mentioned earlier, there's things that'll cart things back and forth, right?
Right. So most ConOps will have to have some mobility agent, so a rover or like a cargo truck that can bring your items from your landing pad or wherever you land your spacecraft to wherever you want to set up your base camp or your work site.
Autonomously or?
Autonomously. Some are autonomous, so like the Lunar Terrain Vehicle, which is a commercial option, has to have both astronaut vehicle control and then autonomous vehicle control when astronauts aren't there.
Since you're working on it, I wasn't sure if you were just going to try to make sure there was a seat for you so you'd have a job to be working on the moon, delivering cargo back and forth.
Yeah, let me hitch a ride on the back.
Yeah. So Jessica, what are you working on in this lab?
So I work with a lot of the different folks that develop the technologies here in the macro lab. We have everything from the LSMS to the Tall Lunar Tower project, precision assembled space structures, and a team that's developing some autonomous capabilities for surface logistics that would work with structures like the LSMS. So some of the things that we're working here in the lab is trying to enhance the fidelity of this testing capability. As you can see, we have some brilliantly green walls. One of the things we'd like to do is actually paint this environment black to help create a more realistic testing environment.
Okay.
Our job as these technology developers is to ensure they're going to work the way we expect them to when we send them to the moon and Mars. And
so what would the black walls do?
Oh, to help create that more lunar-like lighting environment or even in-space lighting environment. We're trying to create an environment that looks like the moon and Mars. We can control lighting if we can control what the environment looks like. Not only are we preparing for things like operations on the moon and Mars, but also just out in space, building structures we need to do critical science and transportation across the solar system.
So with lighting on the moon, it's a little bit different on Earth. And on Earth, it gets diffused through the atmosphere. It kind of spreads around, especially on a cloudy day. You can get nice, even lighting everywhere. On the moon, there's a point source. And then I guess there's a reflection too off the surface. Mm-hmm. So how does that kind of work when you're trying to develop something like this that all needs to be autonomous? Is that a difficult thing to develop here on Earth?
It can be, which is why we turn to other kinds of tools like modeling and simulation, which is the kind of work that I do on a day-to-day basis. So can we create a simulation environment where we can test these technologies in a place where we can control lighting and glare and reflection from the surface of the moon and Mars? So this lab, Macro Lab, offers us an opportunity to test the hardware at full scale under somewhat relevant conditions, but the simulation environments allow us to, control that environment to make it a little bit more realistic than what we can achieve here.
NASA Langley Research Center's role in Artemis is big. We've been talking to a lot of different engineers, scientists. So your team here, just kind of give me the importance of our local researchers and local people helping out with this whole program.
Absolutely. I mean, we are the folks that are preparing for humans to live and thrive on the surface of the moon and Mars one day. There's a lot of critical infrastructure that would be very difficult to build without these kinds of autonomous robotic capabilities. Mm-hmm. And our teams here, folks like Jacob and lots of other friends that we work with, are developing those capabilities to enable safe, long-term human exploration of the moon and Mars.
Wow, fascinating.
Yeah, one of the things we like to say is that robotic systems are a system of a system. So we have lots of different types of careers that work together to make this achievable. So like electrical, software, hardware, structures, all of the team that live in different aspects of Langley all come together to make this a reality.
Yeah. It's a real ISAM family, as we refer to it, in space servicing, assembly, and manufacturing. This is like the best team to work with. And funny enough, a lot of early career folks that work together, but we've been working together for years, from the time we were interns till our big kid jobs at NASA as engineers. It's been a lot of fun.
That's super cool. So in another part of the lab, we're going to take a little break here. We're going to look at the tall lunar tower for power generation on the moon. So we're going to take a look at that here coming up in just a little bit. Welcome back. So we also have to generate power on the moon, and that's part of what the tall lunar tower does. Mm-hmm. What is the tall lunar tower?
Well, we talked a little bit about lighting challenges on the surface of the moon, mm-hmm. where we're sending humans as the South Pole. And year-round, we're not getting more than about 4 or 5 degrees of elevation of the sun above the horizon. Very limited light operations. But the reality is, people are living down on the South Pole without any access to power, without some kind of source. Mm-hmm. NASA's evaluating a variety of different power options, including fission surface power, using nuclear power. But we're also talking about using solar panels. And because of the low elevation of light at the South Pole, that means if we want to have consistent sunlight power around the year, we need to build a tower that's really tall, about 50 meters tall, to have that continuous power access. How are you going to build that tower? That's the problem we're trying to solve.
Okay. Gotcha. So I see the structure of it. It's very, I don't want to use the word sparse, but it is. There's not much to it. But is that the whole point of that?
So one of the goals with the tall lunar tower was optimizing the structure based on how much payload you need to put on top. So if you have a 1,500 kilogram solar panel array on the top, we've optimized a structure to allow us to do that. And that way we're not sending up more mass than we need to have that tower in place.
Yeah, you don't need a tower to hold up giant, heavy things like holding up a bridge. You just need to hold up the solar panel.
Right.
That's what it's designed to do.
One of the nice things is that there's no wind on the lunar surface, so you don't have to worry about that dynamic motion. We do have moonquakes, and so there is some analysis that needs to be done to make sure that those tall towers can survive vibrations like that.
Okay, so vibrations compared to the Earth, moonquakes, are they a little bit more tame, or can they be pretty violent?
So they're not as sudden as Earth, but they are longer durations. So it's maybe there's a lot more work to be done to quantify how moonquakes are, but they are different than what we experience on Earth.
If you build a tall lunar tower at the South Pole, so down from the moon essentially, can it be exposed to sunlight at all times versus if it was towards the equatorial region? Or does it still, in terms of the moon phases, get into a shadow?
So there are certain elevations where you will have a lot less sunlight exposure than others. So what we found is above 30 meters, you have more consistent exposure to sunlight. So everything above that, you could reduce that like nighttime down to 2 Earth days. And
Okay,
then
that's what I was kinda
you
wondering
might
in terms of its
have
orbit, yeah.
still a little bit of occlusion or darkness
Okay.
to deal with.
But you just have to build something super tall at that
Yep,
point, and
so
it'd be really tall.
The higher you go, the more consistent sunlight you will get.
Got it. Okay, and then how many of these, I see in the rendering there's 3 of them, how many do you think would be deployed in the future for a lunar base?
I guess it would depend on how much infrastructure you're deploying. And the Artemis missions, Artemis 3, 4, 5, they scale up in the amount of infrastructure needed to support those missions. So the more power you need for those structures, maybe the more towers you need.
Yeah, and then this would all be for future Artemis missions, ones that we send cargo. We can pack all these things up, and then they would get assembled on the moon, and that's what we were seeing earlier. This would help to deliver that and assemble it?
Yeah, so the LSMS could help deliver some of those packages that you would need to deploy the tower. We also have other systems that would allow us to actually assemble the tower, like the Tall Lunar Tower project, where it's using robots to build the tower 1 cube at a time and then lift it like an extrusion. So then you
That's how it works, okay.
start with a payload and then you build the tower underneath it and you keep lifting it up until you get to the height you want.
So a lot of the work that I'm seeing that you're working on, which is really fascinating, is that this is going to be stuff that's being built on the moon by robots and autonomously. So we're not going to have, the future astronaut climb the tower. Oh, I forgot my socket. Toss it up, which you probably could, but that's not ideal.
No, definitely not, because our astronauts' time is very valuable. We want to use them to focus on NASA's science and exploration goals. So whatever our teams can do to prepare the way for them so that they can just arrive and start working on those science goals, that's our objective.
Yeah, because when you go outside of the base on the moon eventually, you still have to suit up. It's still an EVA type of thing. There's no air to breathe. So it's limited time, and you don't want to be spending that building a tower that could have already been built by something else.
We want to make sure they can use that time for exploration and science objectives.
Anything else that you're working on here that we haven't talked about yet?
Oh, we're ramping up to do a bunch of cool demonstrations. Jacob and his team are working hard to get this LSMS ready for some demos this summer.
Okay.
Some full-scale payload offloading demos. And we're working with teams to do some TRL-4, TRL-5 demonstrations of those kinds of robots that are going to build more complicated structures as well, like those radiation shelters or launch and landing facilities, all those kinds of infrastructure you're going to need to support long-duration human exploration. So we're looking at some really exciting projects coming up here in the near future. So just keep an eye out.
Yeah, definitely will. All right, well, Jessica, Jacob, thank you very much for your time. This has been really insightful to learn what's going to be happening in the future, because we know we have Artemis 2 and Artemis 3 coming up in the days, weeks, and years ahead, but in the future, it's really nice to see kind of what's going to be happening on the moon.
Absolutely.
Good job on your work. All right.
Thank you.
The one thing that I thought was most interesting is just how that spacecraft has to skip across the atmosphere as it re-enters in, with that talk that we had with Kylel. And then, of course, when we talked to Jessica and Jacob, the tall lunar tower generating power on the moon, that's going to be fascinating. And the lightweight surface manipulation system, that large crane thing that we saw at the beginning of our conversation, how they're going to be able to autonomously take cargo off of the spacecraft, put it down onto a platform, and then have another vehicle drive it to where it needs to go. A lot of cool things happening at NASA in regards to the future missions to the moon. I'm really excited to see what's going to happen as we go into the future. Again, a shout out to all of the engineers, scientists, and teams at NASA Langley Research Center and all the centers. Thanks for your time and giving us some more insight on what is going on with the future of these missions. Thanks for watching this episode of Beyond the Forecast.